Pramod Wangikar. I'm a professor at IIT Bombay in India, and I'm a co-founder of Clarity Biosystems, which has developed this software. So the overview of this talk is to look at challenges in metabolomics data analysis, how MSOne was developed, what are the algorithms, how is the implementation. We have analyzed over 100 public domain data sets and placed them in a repository called MetaMine. How the user perceives. So there are two parts of it. What is behind the user interface and what the user is able to see. So I want to briefly present what goes behind the user interface, what's the back end of it, and what's the front end of it. So the user gets to see only the front end. And then if time permits, there are advanced topics. And I also briefly touch upon the data security of this aspects. Mainly, LCMS data analysis, metabolomics data analysis is a cumbersome task usually. The tools that are used, so I have seen, the guidelines or the blogs people, experts have written where there are typically 4 to 6 different softwares are used, and one has to transport data from one software to another. Because there is a lot of noise and uncertainty in the data needs curation. So there is a significant curation burden. While curation is required, many softwares don't allow an easy pathway for curation, and that then becomes labor intensive and operator dependent. There is noise and redundancy, so that needs to be removed. And overall, the softwares present a significant technical barrier. So these were the motivation that we had while developing this software. You may have different analytical objectives and a workflow for biomarker discovery as the analytical objective. But there could be other objectives, and a lot of the analysis pipeline remains the same. There are some minor changes that may take place toward the end of the analysis pipeline, depending on what the objective is. Broadly, the data analysis pipeline can be divided into two parts. One is a pre-processing, where the spectral data or the raw data is processed into a table, and this table typically would have M by Z RT features. So the rows are M by Z RT features, and the intensities of those features in different samples. So that's the typical outcome of a pre-processing exercise. And then the post-processing exercise would take place on this tabular data. This post-processing may include statistics, automated machine learning, or any type of machine learning, or any other exercise. And before you perform any downstream analysis, there is data preparation. So that data preparation is also an integral part of the downstream analysis. While these may be considered seen as sequential, they are tightly coupled. So what, depending on the outcome, you may want to choose, you may, the previous pipeline may get affected. There is also an iterative refinement that is usually involved in this pipeline. And any software that you use must allow that iterative refinement. So MSOne is a software that we have developed which performs end-to-end analysis, so both pre-processing and post-processing. It is vendor agnostic, provides a user-friendly user interface. I don't want to say that there are absolutely no parameters to be tuned, but they are small in number, reasonably small in number. They are intuitive and they are easy to tune. Also, once you tune them for one type of analysis, you don't really have to tune them again and again. You don't need local infrastructure because everything is in the cloud. And currently it is free for academia. The overview of what goes behind. So once you acquire data, the raw data is to be converted into MZML open format. And that data then can be either explored or sort of you can examine that data using various tools in Meta Explorer. So there are 3 apps that are part of MSOne. Meta Explorer is an optional app which you can use to explore your data. Meta Analyzer is the main app that does the pre-processing, starting from centroiding, denoising, peak picking, then peak grouping, feature tagging such as principal ion, isotope, in-source fragment, etc. Then annotation, giving a name to the feature, uh, and that naming can be at MSI level 2, 3, etc. Or even MSI level 1, depending on if the user already has that type of annotation. Uh, and so at the level of annotation, there are two ways to look at it. One is what the software gives you. So the software give you certain annotations, and the user can add or bulk upload their own annotations, so that they can decide whether to use the software annotations or their own annotations. A tabular data is generated, which can be curated using meta-analyzer's visualization abilities. And then that tabular data, once you're happy with that data, then you can take it for statistical analysis on the same platform without having to export or import the data. So the pre-processing algorithms, a lot of these algorithms, as I said, are in the back end, so they are not really visible to the user. The first is in the spectra, there is a lot of noise. So both MS1 and MS2 spectra are denoised and centroided. The user has the option to use MS1 for centroiding, or they can use their own centroiding pipeline and then submit a centroided data. So either way is fine. But if you submit raw data or the profile mode data, then there are certain advantages of of the data that of the centroiding algorithm that we use. In the chromatography, ROIs are generated. And again, this is meant for those who are familiar with the terminology. So regions of interest. These are candidate chromatograms, which are then classified as true signal and versus noise. So noise is removed. True signals or true chromatograms are then taken forward, and peak boundaries are identified using another deep learning algorithm. So CNN is a convolutional neural network, which is a deep learning algorithm. UNet is another deep learning algorithm. RANSAC is an algorithm, not a deep learning algorithm, but it's a regression algorithm, which is robust to outliers. So that there is always a confusion about peak grouping and peak alignment that requires a lot of manual curation. So that is removed using RANSAC algorithm. And then there are a lot of redundant features which could be tagged as isotopes, in-source fragments, etc. So there are certain additional algorithms that go behind it. Some of these algorithms were reported in literature. We have improved them, tuned them properly, and some algorithms are novel. So it's a mix of new algorithms and existing algorithms packaged together. Just to show you how the algorithms work, let's say I have several candidate chromatograms and I want to separate them as noise and peaks. So I will just take peaks that are classified as peaks forward. So this is a shape-aware classification and not necessarily just based on the height of the peak. The shape alone should decide whether it's a peak or not a peak. And for that, we use a CNN, convolutional neural network to do the classification. UNet is another deep learning algorithm that will help you identify the peak boundaries. So all of this happens in what is called as inference mode, meaning the algorithm is already pre-trained on public domain data, and the user doesn't really have to train or figure out what the parameters for the algorithm are. They simply get these peak boundaries because algorithm is running in what is called as inference mode. This is the alignment algorithm, which works with RANSAC algorithm, and it basically identifies what are the outliers. So these are the outliers in this alignment, and they're identified in an automated manner. We have already tuned the parameters of this algorithm for a typical. So this is a chromatographic alignment. Then, as I said, take an example of uridine. It would have an in-source fragment of uracil, an isotope where M+1 is present, an adduct where sodium ion is present in place of proton. So all these can be tagged as the respective ones, and then the user can decide whether they want to include the tagged redundant ions, or they just want to look at only the principal ions. The next thing I just wanted to show quickly is how the MS2 spectra look like. So MS2 spectra also have noise, but we have a separate denoising algorithm for the MS2 spectra. And then after denoising, the MS2 spectra look really clean, and then that not only looks pleasing to the eye, but also improves your accuracy of annotation. So, and then for in terms of the matching score, we have a composite matching score that is based on modified dot product. So dot product is something that most algorithms will use, but we also give some weightage to how many matching fragments are there, number of matching fragments. And then this component goes from 0 to 100, and the second component goes from 0 to 100 to or 120 or so. So as a result, the composite score can go from 0 to 1,000. And what we have seen is that any match that is above a score of 700 is a highly reliable match. The noise gets reduced at every step of the way. So at the end, you have a feature table which is fairly small in size compared to most other algorithms. But that's actually an advantage, because then you have to deal with lesser noise and lesser redundancy in your downstream workflow. How is the accuracy? So there were two samples that had this is a public domain data which is used for benchmarking. So there were two samples, A and B, and the ratio of metabolites in the samples was 2:1. So the log was log of 2 was 1. So the ratio should have been 1. The ratio should have been 2. In all of these cases, we can see that in with MS1 the ratio is close to 1. In some cases, it is either less or the deviation is a lot more. So we have benchmarked against all many other softwares, and we see a significant improvement. How is the software implemented? It is implemented as a Python-based backend and Next.js as the front end. So as I said, the user only sees the front end. Deployed in the cloud platform and parallelized at various levels, so at file, segment, task, etc. So as a result, if you have more files, additional files, it doesn't mean that it will take twice as long or 3 times as long. It scales nearly linearly with the size of the job, but up to certain extent, it actually it's quite efficient because of the parallelization. The deep learning inferences are performed on fixed length segments, and as a result, they are quite efficient. Otherwise, deep learning, as you may have seen in the news, the deep learning and AI is extremely compute intensive and energy intensive. The time taken for feature construction is between 20 to 200 minutes per data set, depending on the data set's size. This is the only time consuming part. So this is something that you would submit and would happen asynchronously. And when the results are ready, you can come back and view the results. So to demonstrate the capability of the software, we have analyzed a really large number of data sets, almost 100 data sets from public domain repositories. And this pre-processed data set is now available in MetaMine. So one can go into this and explore the data sets, perform statistical analysis, perform all kinds of downstream analysis, and so on. These are the 100 studies. The second objective of setting up MetaMine is also a framework for the real users to organize their own data. So typically, a user may have multiple projects. So MS1 is your data would be organized in the form of projects. So each one here, a public domain data set, which is available to the public, is a project basically. So in your private repository, in your private workspace, which would not be accessible to the public, you would organize your data in a similar way, and go into each project and examine it and so on. You will also have the option to share your project, one project at a time, share with your collaborator or supervisor, etc. So the typical user workflow is, first of all, the workflow starts with MZML files. So you would convert your raw data into MZML format and upload that. So once you have uploaded the data, it would be uploaded as files to be uploaded to a project. So you create a project and upload files to the project. Then you would inspect the data using Meta Explorer. As I said, this is an optional step. Once you are done with that, then you can process your job. And for processing the job, you would have to set the parameters. And we have a number of default parameters or the default sets that you can choose from any one of the sets. And then the processing is sort of automated. Once the results are available, then you can come back and visualize the results, visualize the peak quality, MS2 matches, etc. If curation is required, you can always curate it and add user annotations to the data, and that's also fairly user friendly. Once you have the data table, then you want to prepare the data for downstream analysis. That may include imputing missing values, blank subtraction, normalization, um, and any other transformation, etc. Statistical analysis, so all basic statistical analysis tests, feature selection tests, a number of tests and visualization, heat map, volcano plots, all that has been provided in the Metastat toolbox. As you enter MS1, you would sort of be seeing this dashboard, and the software remembers what you did last time, so your recent activity would show up. So if you just wanted to go back to the same project, you would go back to the same project. It would also show you what your statistics is, how much quota was given, how much quota is remaining, etc. And as I said, in this phase, we are always happy to extend quota for those who need it for academic work. Then the all the analysis that you would perform is the server needs to know what data you are trying to analyze. And for this data is a combination of files, a set of files, and processing parameters. And therefore, within each project, you would create one or more processing jobs. So we call it a job. And for the server to know which job you are talking about, you need to load that job. So that's just, you will talk about that job, you load the job, and anything that you perform, you will be performing in the context of that job. Once you're done with that project, you can unload that job, and then you want to process another job or another project, you could do that. You can explore your total ion chromatograms. I will just quickly flash this. You have a feature table in it. For each feature, you will be able to see the MS2 match. You will be able to see, okay, this is, you will, when you process parameters, there are these different options that you can choose from. And you can take any of these and customize that further. So if you wanted to change your mass error, for peak detection, for peak formation, your RT error, etc. So all these can be changed by the user. Then in terms of pre-processing, you have an option of global analysis, which is untargeted analysis, or targeted analysis. If you already have an MYZ RT list of metabolites that you want to process, then you don't have to go through the global analysis. It would actually be much faster to perform targeted analysis. Now, in terms of what output you see, so you have a feature table that will be visible, and this feature table you can apply filters. You can say I want to see only annotated features or all features, etc. So all of that can be done, and then once you have or the feature plot can also be seen. For every feature, as you click on the feature, there are five, as you can see, there are five options here, XIC, MS2, bar plots. You can see any of these, and what is shown here is an XIC for the feature that is selected. And you can see that the feature boundaries, the peak boundaries have been correctly identified for all the peaks, although there is a neighboring or a co-eluting peak nearby. The second option was MS2. So you have seen the MS2 match between the experimental and library spectra. Then you can render the 2D or 3D structure of the molecule that has been annotated. You can see the peak boundaries. You can correct them if you're not happy with them, and you can save the corrected peak boundaries, and the areas would get automatically updated. And right there, you can also see a box plot or a bar plot to examine how the data looks like here. So in statistical analysis, there is a data preparation step. So that involves filtering, missing value imputation, etc., normalization, transformation, and scaling. So all of that, for each of these steps, there are many options that are given. So for example, normalization could be based on median normalization or based on QC normalization and so on. So all you can choose from any of these options depending on what your analytical objective is. You can see a volcano plot, you can see a heat map, a PCA plot to see if the classes are separable, And sorry, yeah. So overall, it's a deep learning enabled processing, you know, which is sort of happening at the back end. It is quite scalable. We have tested it for 1,000 plus MZML files in a single run. It is quite robust to various drifts and corrections can be performed in the algorithm. And statistics and insights can be obtained from the same workflow. We have two implementations of this. One is a cloud deployment, which you will see, if you log into cloud, and this is more for the industry deployment on site. So there are multiple layers of security that have been incorporated, both for the security at rest and security for data in transit. So all the standard security measures have been used. Important feature is a sharing feature. So once I have uploaded a project and analyzed the project, I want my collaborator or a colleague to see that project and see and give, collaborate on that. So I can simply share the project with another user of my choice, and and they can see exactly what I see. So that's a very useful feature. And going forward, we are looking at multi-omics data analysis of. So currently we analyze the DDA data, but now we are looking at DIA and 4D ion mobility data analysis, RAG for as a co-pilot, and pathway analysis.